subject in the world.
Because I don't understand how this works. Like I don't know what this does versus what the air handler does.
Nobody does. It's opposite of how it seems. This little line, these little tubes that connect.
Yeah.
This is, oh boy, that's, hey, just put that anywhere. Make sure you have all this is liquid refrigerant, okay?
Yep.
So this liquid refrigerant flows inside, so it's running this way, down this little tube, goes up to your air handler, and it hits an orifice, which is a really, really small metering device. It meters the refrigerant, and it creates a pressure drop. And on the other side of that pressure drop, the refrigerant expands and starts to boil. And as it boils, it absorbs heat. Refrigerant boils cold. So we're used to water that boils at 212 degrees at atmospheric pressure. Refrigerant boils, R410A boils at like minus 44 degrees at atmospheric pressure. Okay. And under pressure, we can control the temperature at which it boils. So it's starting as liquid, it goes inside to that indoor coil, hits this little orifice, creates a pressure drop, and then it starts boiling, in most cases around 40 degrees Fahrenheit. And so then it starts to boil. And
minus 40 degrees?
No,
or
40 degrees,
okay.
Because it's under pressure. Okay. At atmospheric, it's like minus 44, minus 45, something like that. You with me?
Yep.
Follow me here? So as it's boiling, it's absorbing heat from your house. It's running through that evaporator coil, and it all boils off into vapor, and then it travels back down this larger line, back to your compressor, hits the compressor compresses it, jams all those molecules together, the temperature increases, there's still vapor, and then it runs through this condenser coil, and outdoor air flows over it, and it extracts heat off of it, the heat that, so basically all the heat in your house is coming down this big line. All the heat that was absorbed is coming down that big line, but when you touch that big line, it feels cold, because it's all vapor. It compresses it, it gets really hot, then it expels the heat to the outside air runs over it, and that's where you feel warm air coming out the top, and then it condenses it back down to a liquid, and then you're back to the beginning again. Anyway, where were we at? You're going to edit that out, right?
Well, I don't know. I'm going to edit the whole thing out because it's all garbage.
Right, that's good. Good, thank you.
What I've learned is I am much better at explaining technical topics than you are.
Oh, really?
Yes.
Okay. Wow. I have nothing to say.
All right, I'm going to throw you off. Now what? Now what do you got to say?
I have nothing to say.
That I'm not going to cut out.
What I was telling you, this is the part you need to leave in.
So just, all right, let's start over.
Okay, start
just
over.
explain this simpler to me.
There's nothing to, it's not simple. That's why, because when I say cold, when you say cold, what you mean is in relation to when you touch it, it feels cold. But in air conditioning, everything is turned on its head. It's about heat absorption and rejection.
Explain this without jargon. So tell me how this works.
Well,
so what's the difference between this condenser and the air handler and then the connection, which is the pipe in between? How does that work?
So here's how most people explain it, so that people who have no idea what they're talking about can understand it. But it's not right. That's the problem. Heat is rejected out here, and it's absorbed inside in your coils.
Okay.
And the heat is transferred between these two pipes. And most people think that the cold pipe is pumping cold inside.
Okay.
And then it's making it cold in there, and then it's sucking hot back out the small pipe.
Because the way I envision it, is there's a fan in there, and it blows on the cold coil, which then blows cold air in.
Right. Correct, and that's incorrect completely. That's what everybody thinks. And so, in order to understand it, you have to start by understanding that there is no such thing as cold. Cold is fake. It's just heat, and we're moving heat. And so, the reason the coil feels cold is because its temperature is lower than the temperature inside the house.
Right.
But what's coming into that coil is a liquid line, this little piece of copper here.
Yeah.
It's all liquid, and this is warm when you touch it.
So we have a little one and a big one. What's the little one?
The little one is the liquid line. It's full of liquid.
And that's sending liquid out of this into the air handler.
It feels warm when you touch it.
Okay.
If you've ever grabbed one, it feels warm. When it hits that air handler, it hits an orifice. It expands, and as soon as it expands, it starts to boil.
And that's the big coil thing in there.
Correct.
Right?
And boiling is cold in the case of an air conditioner.
Okay.
So it boils cold, and as it's boiling, just like when you have a burner and you're boiling water, the boiling water is taking heat from the burner and putting it in the water, right?
Right.
In your evaporator, what we're doing is we're boiling Freon, we're boiling a refrigerant, Puron in this case, R410A, we're boiling.
Wait a minute, hold on, let's go back to the water here.
Okay.
So we have a flame.
Right.
The water, we're transferring heat from the flame into the pan, which then in turn heats the water. So the water isn't pulling heat from the flame.
Yes, it is.
I don't know that I buy that.
Well, it's not a matter of whether you buy it. That is what's happening. So water is absorbing heat So a better
Right,
way
right,
to
okay,
think of
yeah,
this
that's
is
fine.
Temperature tends towards equilibrium. All right, all energy states do. So you have something that's hotter, higher temperature. You have something that's what we call cooler, which is lower temperature.
Okay.
All right, but temperature does not equal heat. Temperature is just a difference in molecular velocity. Something that has molecules in it moving faster is higher temperature. Something that has molecules in it moving slower is lower temperature. So what has more heat in it? A little thimble full of boiling water or the entire ocean? What has more heat in it?
The ocean.
Right, correct.
Okay.
There's greater heat content in it, but the temperature is higher of this little thimble, right?
Okay.
So we say the thimble is hot, but really the ocean has far more heat. And so we're transferring this highly dense liquid refrigerant down the liquid line. Okay, it hits this metering device and it starts to boil. And instead of absorbing water from the flame like the pot of water does, it's absorbing heat from your house. Did I say water from the flame? Instead of absorbing heat from the flame, it's absorbing heat from your house into the boiling refrigerant. So all that refrigerant boils in there and it's absorbing heat from your house, and then it comes out this big line fully vapor. And so now it feels cold to us, temperature-wise. It feels cold. But it actually contains all of the heat that's ever been transferred to your house.
So there's air coming out of the thicker line?
It's not air. Air is a different substance. It's vapor refrigerant. So it's refrigerant in its vapor state. And so it comes down this suction line, which is the big line. It hits this compressor, and now because it's got high volume, that compressor then compacts it into tighter volume, and the temperature
and squeezes it back.
again.
Right. Okay.
And so now those molecules are all loose and happy and cool, and you jam them together, and they start going crazy again, and the temperature increases, and now we can turn it back to liquid by transferring the heat out of it from the outdoor air. So it's air conditioners utilize what we call latent heat transfer, which is the heat that's transferred hidden. You can't see it with temperature, but it's transferred because of the change of state from liquid to vapor and vapor back to liquid. Boom. It's a good description. It's just a complicated idea.
All you have to do is lose the attitude, and you got it.
Really? Well, I just have the attitude because it's you.
I know.
That's absolutely why.
Yeah.
What was that?
Nothing?
How was that? Nothing.
Apparently, the attitude is there 24/7.
It's real.
Cut him. Yeah.
Whichever one's
So,
bothering you.
so if I were to take that fat line while the thing's running and I cut it, liquid would come out of it, or vapor. Right.
It'd be vapor.
Okay.
Where liquid would come out of this. This would.
Now I would die, right? Because it's
You wouldn't die. It would just start coming out at negative 44 degrees and it would freeze your hand instantaneously.
okay.
So refrigerant's not poisonous. If it leaked all in your house, it wouldn't hurt you.
Right.
It displaces oxygen. So one time I got high in a motor room accidentally because all the oxygen was displaced. But if freezing refrigerant goes all over your hands, it'll
Right.
give you frostbite, which every AC technician deals with.
So the liquid line is
I didn't use your 3/4, buddy. I used your 7/8. You need mine?
hotter, technically, temperature-wise.
It is higher. It feels higher temperature. So when this thing's running and you touch this, it feels warm. It's slightly higher than the outdoor temperature. So if it's 95 degrees outside, this will probably be 105 degrees. Whereas this line will be average 55 degrees. So it'll be condensating, it'll feel cold, but in actuality, this line has lower heat content in it than this line. This line has the heat already rejected from it in the condenser, and this line is coming back when all the heat's already been absorbed. But when you touch them, they feel totally opposite.
So as it goes through, squeeze it through that little tube, all the way up to, so it's better for it to get there hotter so that it will boil quicker.
There's nothing to do with the temperature of the line at that point. What's important is that it's liquid. What's important is that we've changed the state back from a vapor to a liquid, and
Gotcha.
now we can boil it again.
And
it
simply
will
by
absorb.
changing the state, you'll have a byproduct of heat. Right? The
You'll have
energy.
of heat transfer, correct?
Right.
When we say
Right.
heat, all of the heat that boils the refrigerant is heat from inside your house. That's why it cools your house. Because
Gotcha.
it's taking heat. Heat
So
is
as the
absorbed.
fan is blowing the hot air on the evaporator coil, right, that's what's causing this line to boil.
Well, the line's not, so no boiling is happening in either of these lines.
Right, but I mean that this transfers into the other little lines
Into
in the coil.
refrigerant inside the evaporator coil, right. The evaporator coil is the pot of
Right.
boiling water.
Right.
And instead of you having a flame, the heat comes from that indoor air.
Gotcha.
And so the indoor, because your indoor air is significantly higher temperature than the temperature of the boiling refrigerant. So if the refrigerant in the evaporator coil is boiling at 40 degrees and the air inside the house is 75 degrees, heat's going to go out of the air inside of the house and boil that refrigerant.
Gotcha.
So we're just used to, when we think of hot, cold, boiling, condensing, all these types of things, we're used to thinking of it in terms of air at atmospheric pressure, where we're doing it with refrigerant at controlled pressures, so we can control the temperatures that happens at. And so by how we charge the unit and by how the orifices open and close, we can decide exactly what temperature we want that indoor coil to be, to control both humidity, which is the dew point of the coil, and the temperature of the indoor air.
So now, why are these units superior?
For many reasons. The first thing is these use variable rotary compressors. So a rotary compressor uses a circular motion for compression. I mean, if you think of the old rotary engines.
So is this the compressor on the side here?
No, the compressor is actually inside.
Oh, it's
inside here. That's the heart.
Yeah,
so the thing underneath that blanket is the compressor, and that's what actually compresses the refrigerant. That's most of the amperage, most of the current being drawn on any air conditioner is drawn by the compressor. So this compressor technology is very unique in units of this size. This is a 4-ton system using a variable rotary compressor.
But there's a coil that runs around the.
That's what all these are. So this is a fin pack basically, and you have copper tubing inside of an aluminum fin pack, and this is where the heat transfer happens, and that's consistent amongst all brands. All brands do that, but this uses an electronic expansion valve even for heat mode, which makes it efficient. It has the controls on it are amazing. This thing actually measures its own pressures and what we call superheat and subcool for balancing out the efficiency of the unit.
I notice even the like the trains we took out had like a little circuit board like this big.
Right.
This looks pretty legit.
Yeah, this is what we call an inverter drive, and so it has these gigantic capacitors in here.
Right.
What it's actually doing is it's taking the power coming in, the frequency of the power coming in, and it's turning it into DC. And then it's using that DC power in order to switch and power the compressor at variable speeds in order to produce different outputs, which is good not only for efficiency, so you don't have like a hard start. Most like your old units, when they would start up, they draw up.
You hear them like, after they get older, they go bang, they
make a loud
bang
noise,
into it.
They
right.
dim your lights. So it's bad on the system when they do that. It dims your lights. It uses more power. Where these actually start slow. Even the compressor starts slow, and it slowly ramps up.
That makes sense. Yeah.
Better for energy efficiency, better for longevity. And the reason I really like these units is that variable rotary compressors are proven technology. The Japanese have been using this technology for the last 20 years, and so it's proven. And in ductless systems, it's been used for years. Whereas there's some more cutting-edge technologies that companies have tried that have had high fail rates and have had issues with. In Florida, we have a lot of power inconsistencies, so you'll get brownout conditions and you'll have some issues. Whereas with this particular model, which is the VNA8, the Carrier VNA8, I really haven't had any issues with it.
And that was part of my, what I wanted here was I want this to work. I although this is kind of cool to make videos and learn about, something cool, a very technical topic. Ultimately, I don't want to deal with it, right? I just want it to work.
Right.
I want to go out and polish my car. I don't have to worry about my air conditioner.
Exactly, yeah, and that's just it. I mean, it is a very complex. An air conditioner is probably the most complicated thing in your house as far as all of the different things that go into it. And so you want a system that's going to be technologically sound and is going to be high efficiency, but that you're not going to have to worry about.
Right.
And also the fact these things are crazy, crazy quiet. Not just the core technology, but they have swept fan blades on them and everything.
Which is important because, we do spend a lot of time. This is where, everybody comes in and out of the house.
Right.
And of course, the pole barn's out there. And so these were super loud. Sit right in this spot. This is the back of the house, but I'd almost rather them be at the front of the house because we spend less time there.
One interesting thing is Carrier is owned by United Technologies, which also owned Sikorsky helicopters, and so this fan blade design was pioneered by Carrier based on a design from Sikorsky for a quiet operation. Because a lot of the noise, like the one that you had especially, they weren't actually that loud, but there was a lot of air noise that came out of them. Where this is much quieter on both the compressor and the air noise, from a compressor and air noise standpoint.
So here's our fan, and whatever all that business is. We'll have him explain this here in a second. And then this is where I guess the evaporator coil goes in here.
So this is actually a fairly new thing as well. The evaporator coil is all aluminum. So you have your copper inlet, and the only reason this is copper is so that we can connect to it, because aluminum's significantly more difficult to braze and solder. But you can see the entire thing, all of the tubing is all aluminum.
Yeah, my old one was copper throughout.
And the real big benefit of aluminum is that it doesn't corrode nearly as much as copper does. And so we don't see near the fail rates on aluminum coils. And actually what's interesting is aluminum coils have existed for years and years and years. Carrier used to make aluminum coils back in the 80s. And they've kind of come back to it because there were so many issues with leaks, like what you're experiencing. Whereas this coil isn't going to leak on you. It's not going to have the formicary corrosion that the copper and aluminum coils have. And part of that reason is because you don't have dissimilar metals. Anytime you put different types of metals on top of each other, you run the risk of having corrosion that exists in between the...
So this is the input, that's the output.
Yep, so it goes, and that's what, so that, when I talked about the metering device, the restrictor, that's what this is. This is called a thermostatic expansion valve, or a TXV. And so the liquid refrigerant goes in here, and then this regulates a small orifice inside here that then feeds the boiling refrigerant throughout the...
What the heck is this? Is this copper?
That's copper, yeah.
Why is it yellow?
It's like, I think it probably has a little bit of brass in it, slight alloy. But the body of the valve is all brass. But it's actually, this valve is actually constantly measuring the temperature and pressure of the outlet in order to regulate the inlet. That's why it has these tubes that go to the outlet.
And so that fan just blows air off of here?
It actually blows. So in this particular case, everything's going to be upside down, but but it's actually blowing this direction. So it blows in the opening and then out.
Okay.
Yeah. This is your air handler. Obviously it's downflow, so everything's going to be flipped in this particular case. But this is your heat strip kit. This is a unique heat strip kit. We've got the highest end heat strip kit. It's 3 stages. So it's actually 3 stages of 3 kilowatts.
What do you mean?
So it only uses...
What do you mean heat strip kit?
So this is electric heat, and it's backup.
Oh,
it's secondary heat.
Yeah. Okay.
So this is a heat pump system. So primarily it uses the same process for heating that it uses for cooling.
Just turns it around.
Correct.
Yeah.
So then that coil is no longer your evaporator; it becomes your condenser.
So this is just if it's really cold. This helps to.
Yeah,
helps
take
to
the
aid
edge
that.
off. And it also helps in case the unit ever has to go into a defrost mode, because every once in a while if it gets really cold, the outdoor coil will become icebound and it has to defrost.
And these aren't good for up north because this little thing doesn't. I mean, it's a straight electric, right?
You know, surprisingly though, this technology with the inverter technology makes heat pumps more viable. You're actually starting to see them creep up north.
Yeah.
More so. But yeah, so this is a totally variable blower as well, which you had a variable blower before. They were actually similar technology to what you have now. But this board actually it communicates. This is a fully communicating system, so it's not using just switching. It's actually talking to the thermostat, talking to the condenser in order to decide what the fan speed should be to maintain optimal capacity and dehumidification.
All right, so air is going.
So, this whole thing's flipped upside down, and so air is coming this way. So air is coming. This is the wrong way. It's going to go down.
So we cut a bigger return. So the return is where the air comes in.
Right.
So it's sucking air through the return, up through the unit.
Right. So coil, blower, heat strips, and then out.
And the heat strips are only on if they're on.
Right, which will almost be never. That's why having a staged heat strip kit is nice, because you only use as much auxiliary heat.
So if it's 18 degrees, then
you only need if you only need 3 kilowatt of backup heat, it's only going to use 3 kilowatts.
Gotcha.
All the way up to 9 if it was really, really extreme. But that's the point. Is you don't want to. What a lot of people do that costs them energy is a cold night comes around and they set the thermostat really high. Well, now the thermostat, a traditional thermostat's like, I need a bunch of heat, and it brings the heat strips on.
Right.
Or you don't want the heat strips to come on unless you have an absolute emergency.
Right. So you buried the copper line.
Yep.
So this is what powers the thing on the wall too. So we run a copper line with refrigerant and.
Correct. Yeah. We're gonna
same thing as those over there. We have 2 lines.
Yep. The only thing different here is this is 14.4. So you have
2 hots, a control wire, and a ground. The 2 hots obviously just supply the power.
Yeah.
And then the center wire, which is your control wires, actually works off of DC
Gotcha.
voltage. So pretty cool setup.
Yeah. Why this is different?
Why is it different? Well, it's actually very similar technology to what's in the other systems. It's been around for, these units in the U.S. We've seen them start to become popular.
Isn't this what every hotel room has?
No. The hotel rooms in the U.S. primarily have what are called PTECs, package terminal air conditioners. They're the ones that go through the wall and sleeve.
Yeah.
This is nothing like that. These those are loud and inefficient. These are super quiet and super efficient. And it uses a variable rotary compressor, just like the others. It uses...
Meaning, again, the conversion to DC, right?
Conversion to DC, and it also has, it can run a lot of variable speeds. And these are just super efficient. I mean, this is what the Japanese have perfected. This is the unit that is used in Japan, throughout the Caribbean. I mean, these are the units that cool most people's houses. And those.
Right, and this is what we would do in our house if you didn't have so many interior walls and stuff. Right.
Well,
room by room.
Yeah, we have big houses with all these rooms, and that makes ducting more feasible. But from an efficiency standpoint, this has no duct losses.
Right.
Because you just have the unit inside. In a typical house, you have so much loss just running air through ducts all over the place.
Right. And so here we have the same concept where we have the skinny line and the fat line, right?
Well, it's similar. The only difference is that in this system, the restriction, the orifice, is outside, not inside. So it's actually boiling. The small line here is actually full of boiling refrigerant all the way in, which is why both lines have to be insulated. So these pre-insulated lines, with the gel coating on them and everything, because they're UV resistant, specifically made for ductless systems because they're both insulated. And
wait, so let me think about this. So we have both lines are boiling, so both lines are vapor?
No. So in the other one, you have the big line, which is fully vapor. It's cold, fully vapor. And here, the big line, cold, fully vapor. They're the same. They're both suction lines. They're both coming back. On this system, the line that's leaving is fully liquid. And so it's warm. It hasn't been restricted yet. It hasn't had a pressure drop yet.
Okay.
All right? In this system, the pressure drop happens outside. And the reason they do it is because they're wanting to save space on the inside. They want the inside to be as small as it can possibly be. So they want to offload as much as they can to the outside.
So the coil is out here?
No, the evaporator coil is still in there, but the restrictor is out here.
Okay.
And the controls are all, they keep as much of the work out here, so that way they can keep it smaller inside.
Okay, and this just has a tiny little fan because it's only running one.
Right. Well, and inside they have what's called I think they call a line linear fan, and it's the blower is like that big and like that long. It's this tiny little blower.
Now, is this a new thing for Carrier to make these kind of systems, or?
No, I mean they've dabbled in it for years. They've had relationships with different companies, Toshiba, Samsung. There's different companies that they've worked with, all solid brands. And recently they've started to brand their own product, which is a unique product on the market. You're not going to find this with another brand name on it.
Mm-hmm. Gotcha.
It uses the components that are being used in Japan. Mitsubishi, Samsung, Sanyo, Daikin.
All right. So both of these insulated lines will run up the wall into that.
Right. So we're going to have a line cover on the outside that makes it accessible.
So do we call this the same thing? Do we call this the condenser, and then that's the air handler in the house?
Yeah, we call it the condensing unit and the air handler, but this is the same in that this is a heat pump. So this can become the evaporator, and that can become the condenser in heat mode. In heat mode, they swap, and now instead of, because typically what we're doing is we're rejecting heat out here and absorbing it in there. But in heat mode, now we're rejecting heat in there and absorbing it here.
Very counterintuitive to what you would think.
Right, and that's why it's so hard to describe, because when you touch it, it feels opposite of what.
Yeah, all you have to do is describe it with a smile, and it becomes happy.
Is that what it is? I just need to be happy?
Yeah.
It's your fault. I blame you.
Although we did have an intern one time, you would have loved this guy. He said he would critique. He would come into my meetings with clients, and he would critique. I guess that's what he thought he was supposed to do. I told him to sit there, don't say anything, and just take notes. And so when I said take notes, he thought I meant like critique me. And so I think his critique was that I smiled too much, and you shouldn't do that because when you show your teeth in the wild, it's a sign of aggression. So maybe it's good that you never smile when you're...
Yeah, so because people think I'm too passive right now. I need to become more animated.
Passive.
More aggressive.
No, you were massively aggressive. You need to be less
I
aggressive.
know, that's what I'm saying.
Okay.
That's the feedback I'm gonna get. I know this video is gonna be exactly the same, if not worse than the last one. It's gonna be awful. I quit.
No, you're supposed to say this. Everything's gonna be great.
Oh, everything's gonna be great. That's right. Yeah.
See, there you go. You turned it on there.
Yeah, good. I need to hire you as a coach, maybe a story coach.
No, I'm gonna be your happy coach.
Oh, happiness coach. Okay.
It's like you make me look happy, and I'm like the most angry person in the world. So this is
Hey
great.
man, I'm a tradesman. I'm blue collar. That's what we're just angry all the time.
Yeah, that's true.
Show you my guns and knife collection that I have in my truck. All right, stop filming.
Because what happens when the force pulls you back, your foot naturally comes off the gas. You have to keep your foot to the floor.